Alright, so today we're going to be talking about finding limits using limit properties and finding limits graphically. So we talked about the limit properties a little bit last lesson, but now we're going to talk about the rest of the limit properties. So the limit properties we talked about were the constant, sum, and difference properties, but now we're going into product, quotient, and then constant times a function, as well as rational power. So the main idea that you need to know about these rules is that if you were to take the limit of two functions individually and then multiply them together, you get the same result as if you were to multiply those functions together then take the limit, essentially. Okay? And the same idea with a constant. So if you factor out a constant, so say you have like 5x, you take out the 5, you take the limit of whatever it is as approaches x, then multiply by 5, you're going to get the same result. The constant doesn't affect the limit in terms of calculating it. Alright, so we're going to go ahead and evaluate a few of these. If I give you a limit to evaluate that involves a function, remember I have to give you the information about that function. Okay? So in this case, first thing we're going to do is we're going to replace f of x with 2, right? And replace g of x with negative 3. So that's going to give me 4 plus 12, which is good. So the limit as x approaches c is equal to what? 4. Good. Alright. Next one we're going to do is this one here. We're going to plug in for f of x. So 2 plus 1 to the third power. So what do I need to do first, the power or the addition?
Addition.
Good. So that gives me 3 to the third power, which means that the limit, good, as x approaches c is equal to 27. So a little rule that we use in, like, you're going to see this in derivatives and integrals as well. Once you plug in the value that you're evaluating, you don't need to write that limit step until you get to the end, just because it saves you the time if you have like multiple steps to not have to write it each time. But make sure you put it in at the end, like on a test or quiz. And then the next one, 2 times 2 plus 3 times negative 3 over negative 3 minus 2. So what's the first thing we're going to do here? 4 minus 9, right? Over negative 5. So the limit as c approaches, or x approaches c is equal to 1. Because negative 5 divided by negative 5, right? Okay. A few more examples. The difference with these examples is we're evaluating at a value that goes to x as opposed to a function. So what would be our step 1 for part A?
Plug in 3 for x.
Good. So the limit as x approaches 3 is equal to what? 27. For here, we're going to plug in 3. And if we're doing something more difficult, I won't go this fast, don't worry. What is 3 squared?
9.
Good. 9 minus 9 plus 2. That's 9 minus 4 on the bottom. The 9's on the top go away. And we're left with 2 over 4, which means that the limit as y approaches 3 is equal to what? 1/2. And this one you can probably do in your head. What do you think it is? 3. Does anybody have any questions about how I got 3? Square root of 9. Yeah, they're pretty easy at this stage. I broke it down because I didn't want to rush into it, but you'll see the next lesson we have to actually use some rules and other things to evaluate limits that are a little more complex. But these two first lessons are very easy. So now we're going to talk a little bit about instantaneous rate of change and when it's useful. So say we're in a situation where a limit is or a function is undefined at a point. What's an example of a situation where a limit or a function might be undefined?
It goes like it's the same y point twice, or the same x point twice.
you're on the right track. That would be like it's not a function because it doesn't pass the vertical line test. But like, what kind of function would be undefined at a certain point?
Like a square root
A square
function?
root, good. A square root or like an x in the denominator. We can't have 0 in the denominator. We can't have a negative inside a square root. So say we wanted to get to a point where, now we remember, limits can exist where functions are not defined, right? That's what we've been learning about the last lesson. So the idea is you might want to get really, really close to where that limit would, quote unquote, be defined, to see where the limit is going, because the function is not defined at that point. So this is where we sometimes would use instantaneous rate of change. We're trying to figure out over what interval we can evaluate that. So we have a situation where we're trying to find the instantaneous rate of change of this quadratic function at x equals 3. Which of these 4 intervals would we want to use? That would be most accurate.
The third one?
Good, the third one. Any guess on why we would use this one?
Because if you take the average, those two is 3.
Good, exactly. So the problem with the other 3 intervals is that they're closer to 3 on one side than the other. The distance is not equal on both sides from the number that you're trying to find. Does that make sense? Okay. That one kind of is just thrown in here because there are ones that come up on your digital assignment that I want to make sure I addressed. And then the last one we're going to look at, we've already talked about this rule that the right-hand limit must match the left-hand limit. That's kind of what our whole lesson was about last time. So let's go ahead and zoom in and find the following limits here. So the limit as t approaches -2. So remember, when you're looking to take the limit of something, you need to make sure that where it's approaching from the right and where it's approaching from the left approaches at the same point, and does it?
Yeah.
It approaches at what y value? 0. Even though the function is not defined at that point, does that affect the limit? No. The next one is -1. So if we look at -1, as we approach from the left and from the right, does it meet at the same point? And what point is that? -1. And then the last one we're looking at is 0. Okay. So here and here, do they meet at the same y value?
No.
So the function does not exist. The limit of that function at that point does not exist. Does the function exist at that point?
Yes.
Yes, but the limit does not. That can happen. So on your homework, when you get that, I want you